All right, let's go ahead and get started. My name is Marcus Brown. Today we're going to talk about flow simulation tips and tricks. And before we begin, a little bit about me. I'm a mechanical engineer by education. I'm an elite AE. I was a technical resource for training, support, services, all that kind of fun stuff for over a decade. Now I'm more of a YouTuber, marketing man, kind of, the technical person on the marketing team. I'm a chainsaw enthusiast and a dad. And today we're going to talk about flow simulation, but this presentation is not like an intro tutorial. This is more about troubleshooting and advanced knowledge and sort of getting you that big step forward. And the majority of this presentation, honestly, is driven by user questions on the internet. So forums, emails, comments on YouTube, these are the kinds of things that most people have trouble with or that cause them the most headache. So if you're a brand new user, sit back and watch. I'm going to cover a ton of ground really quick. If you're an existing user, keep an eye out for the details. I'm going to point them out, but I'm not going to show in great detail what it is I'm doing and why. For that, go take a look at a tutorial. This really assumes you already know how to use flow simulation and you're an active user. So we're going to talk about preparing the geometry, something that everyone has to do, but also specifically dealing with complex geometry, right? Simplifying it, troubleshooting anything that might be problematic with the model. We'll talk about meshing, kind of tips and tricks and how to get the mesh efficient and where you want it to be. We'll talk about some complex flow conditions. There's just a lot of stuff. It's almost all going to be focused around one specific case study that has a bunch of problems that we've got to go in and identify and then fix so that we can get a good solution quickly. Let's start with the geometry preparation. Really basic knowledge. Basically, when you start a study, all of the bodies in that study are combined. And if they don't combine correctly, or if they combine in weird ways, or if they don't create the closed volume that you expect, it's going to cause errors. So for the most part, if you see an error, something that says something like unresolved boundary condition, the face is not on the solid fluid interface, you have an invalid face, especially if it's a rebuild error in the tree or the solver errors out on the first time step, that's caused by your geometry. You got a problem, and I'm going to show you how to fix it. Every single body that's in that mesh, hidden or visible, will be combined, and then anything that is airtight will be an enclosed volume. And by airtight, see at the bottom, I either mean face-to-face contact like on the surface or plugged on the inside. Do not give it point contact. I mean, flow simulation may resolve it just fine. It can handle some really weird geometry, but that's not going to give you airtight, and it's definitely going to leave you prone to some problems. The interference fit, which is how most lids are created, is totally fine for the majority of things except for conduction. Main reason being, you don't know the density, the thermal conductivity, and everything else if these are two different materials and they have an interfering volume. So that's the only thing that could cause some weird results. Otherwise, just anything, as long as it's airtight, is going to close that volume in. And specifically, we care about closed volume for internal studies. So an internal study does internal flow only. Internal and external is both. So it only says external, but it's actually internal or external. You can have multiple closed volumes, but the big key here is that for internal studies, you must use lids, you must enclose the volume completely, and you must not have leaks. If you have leaks, you have a problem, you'll have errors, and that's kind of what the geometry preparation is all about. External studies are just so much more tolerant of problems. Now, in an internal study, the domain size is set automatically based on the volume of what's inside the geometry and the enclosed volume that you select. So keep an eye on domain size because it's a clue as to what might be going wrong. In an external study, it doesn't matter because it's completely set by you, so you'll have to kind of worry about that separately. So let's jump into this really complex assembly and see what we can do to try to analyze it. It's going to be kind of a difficult analysis because there's just a lot going on here. Okay, first things first, there is a lid. This thing has slots along the side for airflow. We're going to assume free convection, at least initially. Now, this is sheet metal, so we already know we're going to have a problem with leaks kind of in the corners where the bends don't quite overlap. And in fact, this one, if you'll look even in this button, there's like an opening here. So we've got a lot of geometry preparation to do. Let's take a look inside and see we've got a lot of complex shapes. Now the first one that jumps out to me is the circuit board. This is the one that, you know, usually has the really messed up geometry. And in fact, if you run check geometry on this, we'll run check geometry in a minute, but you don't even have to guess. This is going to be all kinds of problems, all kinds of trouble. So for this, what I recommend is just come in here, grab all the bodies except the board, and suppress them. Just get rid of them. Now, keep in mind, you can always come back and unsuppress that, right? But it at least is going to streamline and simplify. If you get to the point where you're solving a study and that study runs efficiently, then you say, I'd like to have those circuit components in there. That's no problem. Go turn them back on. But always start simple. So our goal is to get this as simplified as we possibly can. So if it's got a lot of bodies, delete or suppress the bodies. What about this guy? This guy has a lot of complex geometry, right? Got these little hex or cross screws. It's got some of these little features, these slots. I'm going to use a feature called D-feature. D-feature is a great way to simplify geometry. Basically what you can do is say, you know, grab all the holes, get rid of all the holes and any other, you know, small geometry, and we're just going to go through and clean everything up quite a bit. And notice I didn't really do much of anything other than say select all holes. It missed these, but you know, there's some weird stuff there. I'm going to just call it good because it really did simplify it a lot. I could take some more time to simplify it and get rid of more detail, but I'm just going to use this. I'm going to create a new configuration. And what this does is it creates a part configuration that is defeatured. Notice that right there. So let's close this out and go back and use that at the top level. And now we have a simpler model. It's not simpler by a ton, but it's definitely better than where we started, right? A couple other methods you might want to use is delete face. So delete and patch does a nice job of removing things like letters, but they can be kind of hard to select all of them. You can use select by size. So this is great if you have small components. Doesn't work on small bodies, but you can say select by size. And with the select by size, you can turn on dynamic selection and then just drag the box up and down until it grabs only the components that you don't mind losing. So like right here, check this out. This is all the fasteners, a couple other little things here and there. It didn't grab all these connectors, but that's probably because those are bodies in a multi-body. So I'm going to suppress all of those. Feeling pretty good so far. I've got a couple other things I can get rid of, but honestly, at this point, I'm kind of to the point where I'm just like tired, right? You ever gotten to that point? You're doing your job, you get to the point where you're like, you know what? Forget it. I'm just gonna go with it. We'll do it live, right? That's okay. I'm going to show you how to do that. Now, you're still going to have to deal with the complexity of all this other stuff every time you mesh, but you're not going to have to worry about it really messing up your solve. All right. So let's go through and start kind of finishing out this thing, getting prepared. I'll show the cover so we can see what's going on, and I've got holes all over this place. I'm going to use the lid tool, and that's going to get us most of the way there. And lid tools, for some assemblies, for some models, that's all you need is a few lids. And the lid tool is really easy to do. You just click a flat face and it creates a solid body. I'm going to grab the outside face here, and then I'm going to grab the inside face over here. And I want to do that just to show you what's going on and make you aware that you really do have to pay close attention to some of the details. So I'm going to click OK. I could have set a manual thickness here, but I just went ahead and left it as the default because it'll usually do a pretty good job of picking a thickness. You want your lids to be about as thick as the rest of the geometry around it. That's just kind of a general rule of thumb. But it's going to build that geometry and drop all those things into place. Now, because it's creating one lid per opening, what I'm going to be able to do is come in here and select boundary conditions and measure flow through each of these lids individually. A lot of times I'll actually create dummy bodies like these lids interior to something. Like, for example, in between two valves in a channel, in a system, in between those two valves I want another pressure drop in the intermediate area. Create a lid there, exclude it, and then you have now somewhere to define a condition or to measure something. But the specific thing I want to show you is, because this is a thin wall, and because I use the lid tool, we have some consequences that we have to at least understand, if not sort of deal with. This first one, I picked the outside face, and what it did is it did an offset entities to the outside, made it a little bigger, and then extruded it down through, so it created an interference. That's okay. I'm not doing any conduction on this lid, so that's not going to create any problems there. But it did poke through the other side. And so now I have multiple faces that are going to be considered boundary conditions, whereas on the other side, I grabbed the inside face. And so now that's a lot simpler. If you ever see a face that's sort of halfway in, halfway out, don't worry. Anything on the outside is just going to get ignored. You're just worrying about what's on the inside that's touching the fluid, right? That's where those errors about not on the fluid solid boundary comes from. All right, so I don't love these lids here. These lids right here, these first, 8 lids. And so what I'm going to do is just delete those because they're honestly they're poking through and not exactly giving me what I would like to have. And so I'm going to come in and try something else. Here's another method you could use to close these in. You could just take anything, any part, like this front panel, just grab it, made it into place, and there you go. We've got a lid. Now, is this a good lid? Sure, sort of. Couple problems with it. I only have one face, so it's easier to define where the lid boundary condition is, but I can't individually specify or measure flow through each of the individual lids because it's one big lid. So that's some pluses and minuses. The biggest problem I see with this guy is that it's going to make my domain much bigger than it needs to be. So it's definitely not what I want. It does not matter what you use to close those pieces. As long as you close them, you're going to be good to go. So I'll finish this one out, just select the inside. But we already know this is not going to be the end of it. We already know that these slots are not enough to close this volume in. We've got knockout holes down here. We've got screw holes where the screws got removed. We've got slots in the sheet metal, all kinds of stuff that we need to fill in. And here's the thing, if you don't know where the leak is, it can be maddening trying to find the leak and patch it and fill it and lid it, whatever you need. So I want to show you a trick. It's a really simple tool to use. It's called leak tracking. And the way leak tracking works is you pick a face that you know is on the inside of your domain, you pick a face you know is on the outside of your domain, and it'll connect the two, point A to point B, showing you in the process where the leak is. So I could grab like the front and back of a lid, right? But I'm gonna make it a little bit more fun. I'm gonna click this face and then this face. So what I wanna know is how, if I was leaking air, I would be able to draw a line in 3D space from here to there without going through any geometry. So I say find connection, and it just draws, it actually draws it on the geometry. It doesn't go through like 3D space. It kind of just circles or follows the edges. And it kind of uses a weird algorithm, so sometimes it'll draw it in a really weird way, but check it out. It goes down, connects to the back face, goes up that back face to the corner, and that's where the leak is, right? So simple and easy to use that tool. Now I got to figure out how to close this in. So this used to be something I would tell people, oh man, you know, closing in an electrical enclosure with sheet metal is tough. You got to use like closed welded corners. You got to modify the geometry so it's actually fully enclosed. But there's a trick that I've been doing with these, or things like this, that I just absolutely love, and I want to show you. And to do this, I'm just going to create a new in context part. And a lot of times this is what I'll do to create custom lids. I'll just come up there to insert components and say new part. First thing it's going to ask you for is a plane to attach it to, and I'm just going to grab the front plane, or you could grab the outside face of the enclosure, whatever you want. But the key here is you're going to create a box, and you're basically going to pick, you know, somewhere out here, the outside, so that you're way outside those lids. You don't want to overlap your lids. And I'm going to create a box that is at least enclosing my interior volume. Extrude that out, and for this one we'll come all the way out to here. And you can make it a little bit bigger if you need to, but basically that right there is the volume that I don't want the air flow to leave. In other words, I'm going to seal all leaks that are inside that volume, and to do that I'll just shell, and I'm going to shell outward. And what it does is an outward shell just creates a wrapped box. So basically just wrap this thing in a box around the interior volume. Now, does this exist in real life? No. No, it doesn't. But in real life, I'm not going to be concerned about that, because in real life, these are all going to be filled with wires. These corners are all going to be welded, or even if there is a leak in real life, it's not going to be a consequential piece of this study, because I'm looking at free convection on this transformer generating heat and radiating it up to these contactors in the circuit board. So if I was to now look to see whether or not I've got it airtight, I know I do, because I literally just created the dumbest, simplest block ever. Let's test the theory real quick though. So I'm going to suppress this, and that's just that box. It's already hidden, so it doesn't do anything, but I'm going to suppress it and say check geometry, and I'm going to say it's an internal study. If you have a study already created, there'll be a checkbox in here that says exclude volumes with no flow conditions. That would allow you to get a false negative, so be real careful about enabling that option. But I don't have a study created yet, so that doesn't show. I'll click the check button. It goes through and it merges all those bodies. This is going slower because I have all these connectors and all this other stuff in here. But it did tell me, hey, this is not a watertight model. So it failed, conclusively failed. It does say it's a 0 fluid volume and the analysis is internal. Now sometimes this will succeed, but then your fluid volume is really small. When that happens, that's a false positive. It did not succeed. What it did is it found something, but not what you want. So let's redo the check geometry with that part unsuppressed. Internal study, check it. Now all the leaks are going to be completely sealed, right, inside that sort of that shell. It's successful and has a non-zero fluid volume. Now I highly recommend using units that are intuitive to use so you understand what that is. 0.006 cubic meters is probably about right for this, But if you're not quite sure, show fluid volume. See this button right there, show fluid volume, and it highlights the volume that is fully enclosed. Notice you can see the resolution of the lids. That's good. That means I didn't cover up the lids with that block that I created, because that's definitely a concern. But you can use that on almost any generally regular shape. All you're doing is just saying, look, I don't care about the little slots. Just close the thing up. There is another easy button for these kinds of scenarios. I'll show you that in a second. But we're ready to roll. We've now simplified up to the point of our patience. we're done doing that. We're not really interested in spending more time cleaning that up, because you can spend all day cleaning up geometry and never really get anywhere. So what I want to do is create a study. So let's create a brand new study. I'll go into my flow simulation wizard. I've already got my flow add-in turned on. And I'm going to call this internal heat-free convection, because I'm going to use one later that has a fan in it. So next, we'll leave SI units for now. That should work. We need fluid flow because it's in the atmosphere. We need conduction because we're doing heat transfer. Radiation is not needed. It's not a super high temperature differential. I'm not doing a transient. I just want to do a steady state, but I do need gravity. Common problem I see here is that the direction is wrong, right? It's in Z instead of Y. So I usually just come in here and Control X, right? And then Control V on Y, and that same value is there. So I don't have to type it in. For the analysis type, we want to do this as an internal. If I said external and then I ran it, it would create a lot of extra fluid around it, and it would solve it out there and take a lot of extra time. And it would ignore any of those errors in my geometry if I still had them and hadn't fixed them already. For geometry recognition, this is kind of a new enhancement. I'm still kind of getting used to exactly what this does and doesn't do, but effectively it's a different mechanism for deciding what is or is not an enclosed volume. So pretty handy. Use that if you're really dealing with a lot of contact issues. And then exclude cavities without conditions. That's that option I told you about in check geometry. Just be real careful with that, because if you don't put in a condition and you start doing things like meshing and checking geometry, it'll fail because it says, no, there's no conditions on this volume, so therefore it's not a volume, therefore I don't have a volume, therefore it can't work. I'm going to turn it off just because I already know there's no internal volumes, so it doesn't matter. We're just going to keep this real simple. We'll say air, and we'll say mild steel. For the metals, they're almost always, I find them under alloys, not under metals, which just kind of a weird thing. So mild steel, ambient air pressure, the pressure potential with gravity turned on and these holes being vertically aligned, we do want to make sure that's enabled. So here is our first look at the domain. I mentioned this a little bit up front. The domain is set to be automatic based on the geometry that you pick. So if I take a look at the front view here and I zoom in, you'll see that because conduction is enabled, it goes all the way out and fully encloses all solids. If conduction was not enabled, it would fall pretty much right about the same shape as that dummy body I did that sealed all the openings. So you would see some solid outside the domain. So if that doesn't match up with what your expectations are, that could mean you have a problem that you don't even realize yet. Now when I look on the back side, check this out. I've got all this empty space. Now flow, there's a whole lot of things that it can handle. It can handle empty space, it can handle weird geometry, it can handle all kinds of problems. But what you don't want to do is waste computational time, and I don't want extra space back here. Now it's not obvious what's back here, but if you do a box select right to left, that's a crossing. Anything touching that box will be selected, and what it does is it grabs those cable glands. Right? So there's something going on with those cable glands, and if you open them up, right, just like the circuit board, you could come in here and you could get rid of whatever the other bodies are. In this case, it's a hidden body that was created by whoever built this gland, and that is where the wire is going to come out. So these are probably part of routing. The wires are going to come out of there, kind of a starting point for the location of the wire. We don't want to get rid of that or else this thing won't function. But it's hidden because we don't actually want it there. So how do we get rid of something from our study without modifying the fundamental geometry? Because we don't want to do that. So I said everything that's included in the study gets merged and then meshed. But what if it's not included in the study? That's where you need to know about component control. Right-click Input Data, Component Control. And here you get to tell whether a part or a body is enabled or disabled. So for example, these cable glands have that extra body that I don't want. I can disable them, and it's the same as effectively suppressing it in the model, except that I have not modified the model. I've only modified the study. So I'll hit apply there. Sometimes I'll put in lids in areas where I just want to measure something of value. I'll put a lid kind of in the middle of nowhere. I don't want the fluid to move around the lid. I want it to ignore that lid, because that lid is only there for perhaps a goal definition. Perhaps it's a measurement face. Maybe it's a mesh control, which we're going to get into in a little bit. In those scenarios, you need to disable that body, and when you do that, the fluid will go right through it as if it doesn't exist. So anytime you have geometry that exists that you don't want, exclude it and get rid of it. Get it out of your way, out of your life. All right. So now that we've got the domain cleaned up, I'm going to go ahead and do one more quick change. And I'm specifically waiting to do this till this point, because at this point now I have a study created. I'm going to go open up this component, and I'm just going to get rid of these connectors. I was doing this earlier. I thought, oh, those are just kind of bugging me. I'll come back and I'll do them now. What you're going to see sometimes, especially when your add-in is enabled, is that you're going to get these messages that say the system has been changed or something is being reset. Do you want to reset the domain? And in this case, like if I come in here and move some of these around, that's going to create some problems for me. In fact, for lids, I'm going to undo that move. For lids, I usually recommend you just come in here and fix them all so they don't move, or add mates as needed. But if you go in and you make a change, this is likely to happen. The model geometry or project settings have been modified. Do you want to reset the computational domain? So the answer to this question in this scenario is yes, because I fixed that body on those glands, and I want the domain to be recalculated. You can do that manually if you want to. It's totally up to you. But if you go in and you set up something like a symmetry condition or periodicity, or you manually set the size of your domain, or you customize something, do not click yes, because that'll throw away all the work you've just done. Okay? I usually don't tell it to remember my choice, because sometimes I do want it to reset like this, and other times I don't. Now here's the rub. If you leave the flow study on, or the flow add-in on, and you have your study open, this thing's going to bug the tar out of you. It's going to just non-stop be bothering you. So I recommend, if you've got a lot of changes to do it before you create your study, or turn your add-in off temporarily, do all your work, come back in and let it rebuild the domain, and then it may also reset the mesh. In this case, I didn't really have anything going on in the mesh, but I can reset the mesh settings, which resets the basic mesh and everything else that goes along with that. All right, so I now have a closed volume. I have a flow study. I need a condition. Let's just do a couple conditions real quick. We'll create a boundary condition, and I'm just going to create a pressure opening where all these lids are. I do not recommend using environment pressure. Why don't I recommend it? Because it does some weird things. It's static pressure in one direction, total pressure in the other. Meaning coming and going, you're going to get different pressure values, and it's not going to match up to what you expect. So if there's not significant pressures caused by moving volume, moving air, I always use static pressure. Okay? You'll almost never go wrong in that scenario, and the only thing environment pressure is giving you is sort of the additional pressure of displacing air that's not modeled in your study. And if it's that important that you know how the displaced air affects your pressure, you probably should include that in your domain, which then allows you to go back to static pressure. All right, so there's my static pressure openings, and I just grabbed all the bodies. That's a really easy way to avoid any kind of a problem where it says, oh, that face doesn't lie on the boundary. Yeah, I didn't click the face, I clicked the boundary, or the body. So lots of little tips in here. I know I'm going super fast, but that's why we're going to get this up on YouTube so you can rewatch it at a later date. All right, let's create a mesh. And when I go to create my mesh, what I want to do is take a look at the default settings so far. And when you come in initially, you've got this Happy Fun Time slider bar. I call it the Happy Fun Time slider bar because it doesn't tell you anything. How accurate do you want it to be? 3. Yay! How about 4? Awesome! Now what is 3 versus 4? Well, it's actually quite a lot of things. So I'm going to show you what that is and how that works. But here's that close thin slots option. That is the perfect thing to use for sheet metal if you don't want to have to put a big old box around it. Close thin slots cleans all that up. But I don't need to do that, so I'm not going to mess with it. All right, so level of initial mesh, the default value is 3. I'm going to jump into the manual mode. In manual mode, it starts wherever you left off. So if you picked 5 and then jump into manual mode, that's going to be 5 as a starting point. Now usually a number 3, what it does is it gives you a basic mesh, looks about like this, tries to keep the squares as close to an aspect ratio of 1 as possible. Usually the default values are level of 2 refinement on narrow channels with a characteristic number of cells of 5, advanced refinement of 4, and tolerance level of 5. That's usually the default values, although it'll update as you start using it. It might switch over to a different default starting value. This is a problem, right? Let me talk about what exactly meshing is doing and why it's so problematic. When you do a mesh, you start out with a basic mesh. Each element in that basic mesh is one element, one data point. And if you refine that to level 2, you split that in 3 directions, right? So 2 to the 3rd power is 8. Now, if you were to split all of those again, you would hit 64. Now, that's only 2 refinement levels up. We're now 64 times bigger. And every time you go up another refinement level, your mesh count starts to explode exponentially. This is what can create massive meshes. This is one of the reasons you want to simplify your geometry, but you don't have to do geometry simplification to achieve an efficient mesh. And here's the key: we need an efficient mesh. We're not ready for a final solve. This study is not set up and ready to give us that solve that takes all afternoon or all night and gives us a super accurate result. We don't have confidence in this study at all. So we need a very efficient mesh to start with. Then go back and do things like unsuppress all the components on the circuit board and run it all night and do all that kind of fun stuff. So this is what the meshing dialog looks like, and I'm going to try to explain meshing and mesh controls in flow simulation as a balance between what you want and what you have to offer. So, for example, narrow channels. That's the very first mesh refinement characteristic that you can set. 5 is the characteristic number of cells across a channel. Those slots on the sides of the enclosure where I'm going to put my pressure boundaries, those are channels, right? Two opposing faces separated by a gap. So what I'm telling it is I want 5 elements to, cover that gap opening. Now that's all great, right? It's good to want, right? Wish in one hand and refine in the other. You're going to have to refine from your basic mesh a certain number of times to hit that number. How many times do you have to refine? I don't know. But what I've done here is I've said 2 is the refinement level that I am willing to give. I have 2 refinement levels to give to the channel refinement strategy. So if you see a channel and it has less than 5 elements across the channel, refine it up to level 2, but no further. Okay? Doesn't mean I can't go beyond level 2, I just can't from a channel definition. And so what really gets complicated is your elements are going to get meshed based on multiple overlapping criteria that may or may not actually be solved correctly. So let's say that I want 5 elements across a channel, but I don't have enough refinement levels to achieve that. I could filter the channel types by size, but let's go down to advanced refinement. Usually it starts out where it says small solid feature refinement is at level 4. That's significantly smaller of elements, right? Larger refinement level than it is on the channels. In fact, to the point where I would almost say you don't need the channels. You could turn that off and it would probably have 0 impact on your results. But refinement level 4 means if I see a sharp corner, I want refined mesh around that sharp corner because that's where flow is going to kind of circle around and kind of hug that corner. So it'll refine it up to 4 times. The last one that's enabled is down here. This tolerance level is 5. If I have a bumpy surface, even just a really small divot, like embossed text that's just a thousandth of an inch thick, I can go up to a level of 5 to refine that and get a good mesh around that text. Now, do I care about refined text? No, I absolutely do not care about embossed text. So like this reset button around these screws and stuff like that, I'm expecting a really tight mesh in those areas. Just for reference, let's go ahead and mesh this because I want to show you, and this is something I really recommend you do. Don't solve on your first run, just mesh. So you uncheck the solve button, let it run, and what you're looking at is kind of the top line number, the total cells. At this point, I'm going to try to sort of cheat and shortcut the system by leaving a lot of my geometric complexity in the model, but then just telling it not to mesh it. Right? That does mean the mesher is going to take a little longer because it has that geometry to mess with, but the idea is, the hope is that the mesh sort of just glosses over it and it doesn't really worry about that. All right, so if we take a look at that, we can look at it in the solver window, or we can look at the summary, but total cells is 596,000. So almost 600,000 total cells that we have to deal with. And that mesh took quite a bit longer than I would like it to. Let's take a look at the mesh. Now you can show your basic mesh here. You can go to this mesh node and show it. But my personal preference is to just create a cut plot because it makes it easier to explore. So what you do is it's a mesh plot, hit the detailed preview, the little eyeball here, and then you can drag it up and down and try to figure out what's going on. Now let's look at kind of the front of this contactor here. And you can see it's got a lot of refinement right around the edges of these holes, right? In fact, if we look at the basic mesh is here. That's a 1, 2, 3, 4, 5. So it went to the full level 5 all around all these little features. So one solution to lots of refined edges is to clean it up like I did on this one where it removed all those slots. But that's just not always feasible. What I want to do is tell the mesher to just ignore boring little areas like this that don't mean anything. All right. So that's a problem I want to fix by reducing the complexity there. Let's take a look and see how it resolved around these slots. And I've got 1, 2, 3, 4, barely 5. But look, it's not doing it because of the narrow channel refinement. It's because of the small solid feature refinement level. The channel refinement did not achieve its goal. So not really where I wanted it to be. I did not achieve what I wanted. I'm going to go ahead and click OK on that, and I'm going to go fix this. And I really do. I recommend you do this and clean this up. It's going to save you so much time down the road as you go. So let's do this. Let's say if I was to increase the channel refinement level, that would fix the ability to refine these slots at a higher level. But remember what I said, a channel is two opposing faces with a gap in the middle. Every slot, every opening, every hole, every gap in between any of these connectors, those are all considered channels within the eyes of flow simulation. So increasing the refinement level for channels is likely to give us the same result as that small solid feature and just give us all kinds of more problems. So I'm going to leave it at 2. 2 at least got us close. But for advanced refinement, I don't want small solid entities refined to high detail. I'm trying to just get overall macro flow, meaning the action is mostly going to happen in the areas where there aren't any solids. So I'm going to turn this down. And in fact, I'm actually going to turn it off. I'm going to set it to 0 for the tolerance and the small solid features. But what I am going to do instead is I'm going to refine all fluid cells one time. Again, the area that I care about is open areas, which would theoretically be at a refinement level of 0 by default. Let's kick that up to 1, turn all the other ones down, and I'll click OK. Now that does not necessarily give us what we want as far as refinement in our mesh, it doesn't give us what we need for refinement in our lids. So I'm going to create a local mesh, right? Local initial mesh. And with the local initial mesh, I'll just grab all my lids and say that everywhere there's a lid, I want, let's not go 5, let's go 7. And you can use up to 3 characteristic or 3 refinement levels to get there, to achieve that number 7. Component control. Remember I went in and I excluded those little dummy wires on those flanges. If you create a local mesh or a rotating region or an internal lid or anything like that, you have the option to disable the solid components as you're using it. This I don't want to do. I want these to be included so that I can use them as boundaries and then use them as part of the enclosure of the model. So I do not want to disable these. But let's say, for the sake of argument, that I wanted to create a volume in here where I knew there was a lot going on and I wanted to refine that level independent of the rest. What you'll do is just create a dummy body, right? Just extrude a block or a cylinder or whatever you want. Drop that sucker in there right through the middle of that area. It's then going to be excluded from the component control, and then you can use it to choose to refine your mesh more. You can use it to change some settings in something. You can use it as a filter, a porous media, whatever you want. So let's run this one more time. I'm going to manually tell it this definitely needs to be mesh. Sometimes you change a mesh setting and it doesn't recognize it's new. So you want to make sure to check the box that says mesh to make sure that that thing gets remeshed and updates with, we got a lot less solid refinement level, but we got a higher refinement level only on the lids. And this one's going to solve quite a bit faster because it's not going through and having to do refinements on every single face. And it flashed up there real fast, but basically instead of 600,000, now I'm at close to 100,000. And if I show my mesh, you can see that everywhere in the open, it's got a better mesh than it did before. And if I come in here and I look at my lids have a much better refinement level there. These are actually refined along the walls because the basic mesh has to only refine by one level at a time. And so these guys had to be split so they could be split again. That actually could be adjusted, but honestly, this looks pretty good, and I'm not seeing a lot of wasted effort around these areas of detail. So this right here, this is an efficient mesh that's ready to iterate quickly. And then once I'm done, I can go ahead and unsuppress and add complexity back in, knowing it's going to solve okay. So let's apply our flow conditions. So let's say I've got some complex conditions in here. I want to create a fan, and I want to create a heat source. Well, if you go to your input data, you don't see those in the tree, right? Right-click at the top level, customize tree. This allows you to turn on additional complex values, such as heat sources and fans. And so now with heat sources available, I'll say insert a volume source. I'm going to put 100 watts on that transformer. We'll call it good. As far as the fan is concerned, I can come in here and drop a dumb body, a dumb solid if I want. Or I could even identify some of these as fans. And in fact, fans can really be defined anywhere. So in other words, if you want like an external inlet fan, I could click this face. And you and I both know that air cannot get to that magically, but flow doesn't care. It's just going to bring air in from here. So fans, internal fans, you need two faces. So I could even say fan gets sucked in here and then it gets magically blown out this face. Is that actually how that works? No, but fans are actually pretty cool because they allow you to, well, that's an internal fan. They allow you to basically just make stuff up as you go. All right, I'm going to leave the fan off for now, and we're going to go ahead and get this ready to solve. The assumptions that are going on when you use a fan, when you use a heat source, when you use any of these other values, two resistor components, heat pipes, electrical sources, transfer boundary conditions, there's a lot of stuff in here that's pretty complicated. And there's a lot of scenarios in the world that are complicated, such as multi-phase flow or particle studies or mixing of fluids of relatively different viscosities or extremely high or low pressures or velocities. And so if you have something weird, whatever it is, I want you to know about these PDF documents that are on your hard drive when you install Flow. There's 3 of them: the technical reference, tutorials, and validation examples. So if you have Flow, especially if you're a student, you have Flow, you're trying to figure out how to use it, and you just have no reference. Maybe you're trying to do a rotating geometry example. Go into the tutorials. There's a example in there with rotating geometry. It shows you how to set it up. They give you the model, everything you need, explains it along the way. It's great. It's the next best thing to training. The validation examples is kind of more like just basic, simple examples that have known solutions that are then solved in each service pack and each release of the software to make sure it's accurate. You can actually do your own checks. Say, well, is this solving correctly? Is this giving correct answers? You can open up the models and check for yourself. But the big one is the technical reference. It explains the assumption, explains the formula, explains the coefficients, and it tells you what is and is not available. If it's, for example, cavitation, it explains what goals to set in order to be sensitive to the existence of cavitation to make sure that the solver does not terminate prior to fully developed cavitation effects. So There's just so much there. I can't possibly cover it all. But if you ever want to know, hey, I wonder if Flow can do that, that's probably where you want to go first to find that out. But with that, I'm going to stop here and open it up for questions. That was a lot of information. I know we went through a ton of different things. Every project you do is going to be different. Every single challenge you encounter is going to be different. But my hope is that with these tips and tricks, with some of the practices that I showed and recommended, hopefully you'll be able to identify them, find problems along the way, and save a lot of time and not really waste it sort of struggling with a model.